Okay, let's take roll. Get this class started. Today is the 24th. Okay, answer your names, please. I see that Miss Hersey is here. Rani is not here. Kilcrease is here. Lucky, I don't see Lucky. Luna Sanchez, I don't see her. Macias is not here. Morris is here in person. Powers is here. Renfro, I don't see Renfro. Salvador, I don't see Salvador. Oh, I skipped McKinnon, he's here. And Spivey is here, okay. Okay, all right, so the last time we were here, we were working on problems in assignment number 5. And there are 2 remaining questions that we did not get to, which we're going to discuss right now. So let me bring this up. Oh, of course, I need to share my screen with my students out there in Zoom. Okay, so number 9, question number 9 in this assignment. And there's another question after that we need to look at. So let's see what question number 9 is all about. It talks about the complex that is formed between iron 3 plus iron and the cyanide ion to form this complex here, FeCN6 3 minus. To be perfectly honest, I don't know what the name of it is. I know that there's some rules, IUPAC rules governing the names of these complexes. So in any case, the question says that in a 0.011 M solution of potassium cyanide, the equilibrium concentration of Fe3 plus is 8.5 times 10 to the minus 4 M, and that of the complex is 1.5 times 10 to the minus 3. So the question is asking for you to calculate the overall Kf for this complex, all right? So let's first write down the equation for the reaction, and that equation is Fe3 plus 6Cn minus to form, and this is a reversible situation, to form FeCN 6 3 minus, all right? So that's a equilibrium system right here. Now the question gave you the concentration of the potassium cyanide, which means that the concentration of the cyanide itself would be the same, which would be 0.11 M at equilibrium. The concentration of the Fe3 plus is given as 8.5 times 10 to the minus 40, and the concentration of the complex FeCN 6 3 minus is equal to 1.5 times 10 to the minus 3. So the expression for the Kf for the complex would be the concentration of FeCN 6 3 minus divided by the concentration of Fe3 plus times the concentration of the cyanide minus raised to the 6. And then we plug the numbers in. So for the complex, as we said before, its molarity is 1.5 times 10 to the minus 3 divided by the concentration of the Fe3 plus, which is 8.5 times 10 to the minus 40, multiplied by the concentration of the cyanide, which is 0.11 raised to the 6. And when I did that calculation, the answer I got is 1.0 times 10 to the 42. And that's basically how that is done, all right? And as I said before, if you recall, I said that typically the formation constants for complexes, such as the one that we're working with here, are typically very large. As you can see, this is a very large number. 1.0 times 10 to the 42 is a very huge number, which reflects the stability of these complexes. These complexes are very stable, and therefore the formation constants for them would be very large. All right? Okay, so that's basically it as far as number 9 is concerned. Any questions about this one? Any questions? Any questions? Okay, so I take it it's okay for me to clear this, so let me do that now. And then let me scroll down to the last question in this assignment, and that's question number, I might need some space, some more space for this. Let me try to work with this here. Okay, so in question number 10, it says that the KSP for silver bromide is 5.3. Turn on the pen function here. Right, so the question says that the KSP for silver bromide is 5.35 times 10 to the minus 13. And it says calculate the molar solubility of silver bromide in water, all right? So in the case of silver bromide in water, we did an example of this already. So basically, this will give you Ag plus Br minus. So if we write down the ice table, this would be 0, 0. And then the change would be plus S, if S is the solubility, plus S. So at equilibrium, we're going to have S and S. So therefore, KSP would be equal to S squared, which means that S would be equal to the square root of the KSP, which would be equal to the square root of 5.35 times 10 to the minus 13. So let me get my calculator out. And please, as I always say, check to make sure I'm doing the right thing, because of course I'm subject to error. 5.35 times 10 to the minus 13, and then we find the square root of that. And according to my calculations, this works out to be equal to 7 point, how many sig figs? 2 sig figs. 3 sig figs. 7.31 times 10 to the minus 7. M, all right? So that's basically the answer for this part right here. So let me just write down here, because I want us to compare this answer to the answer for the next part, all right? So that's the solubility of, 10 to the minus 7. That's the solubility of silver bromide in water. Now the question says, continues to say, that silver forms a complex with ammonia, and it gives you the complex formula, and the Kf value is given as well for that complex. So the question is asking for you to calculate the molar solubility of silver bromide in 1.5 m ammonia. And this time the question is also asking what mass of silver bromide will dissolve in 175 mils of 1.5 m ammonia. So I must apologize. I should have divided the questions into several parts. This would be the A part, this would be the B part, and this would be the C part. All right, so let's go along with that. All right, now let me erase this part right here. So I'm going to write down 2 equations. One equation is for the dissociation of silver bromide, which we had before. So that dissociates to form Ag plus Br minus. And we know that the KSP value for this is equal to 5.35 times 10 to the minus 13, all right? And then now the silver ion here will react with ammonia, 2 moles of NH3 for every 1 mole of silver, to form the complex, which is Ag NH3 2 plus. And the Kf value for that is 1.69 times 10 to the 7, all right? Now, if you add these 2 equations together, the silver ions will cancel out here and here, right? So what will you be left with? You'll be left with Ag, Br in equilibrium, plus 2 NH3, I'm sorry, in equilibrium with Ag, NH3, 2 plus, there should be 3 here, plus Br minus. So my question to you is this: how would we determine the K value for this overall equation? you remember from 2 chapters before this one, remember what we said about determining the K for one equation, which results from the addition of 2 equations. Exactly. So therefore, I don't know if you guys out there in Zoom heard, but Ms. Morris told me that we should multiply them, which is actually the case, right? So basically, K here would be equal to, let me do the multiplication here, 5.35 times 10 to the minus 13, multiplied by 1.69 times 10 to the 7. And according to my calculation, this works out to be equal to 9.04 multiplied by 10 to the minus 6, all right? So that's a K for the overall reaction. Now, this is going to help us now to answer the question in the B part, right? Because what the B part is asking is for the molar solubility of silver bromide when dissolved in, or when added to ammonia. So I'm going to need some space here again, so I'm going to do some erasures here. So let me erase this here. What I'm going to do is rewrite the final equation that I had before, because what I'm going to do is write down an ice table associated with that equation. So the equation I had before is AgBr plus 2NH3 to form the complex AgNH3 2 plus Br minus. That's the equation. And the Kf value that we got for that was 9.04 times 10 to the minus 6. All right? Okay. So what I'm going to do now is set up an ice table where the initial concentration of ammonia is 1.50. The initial concentration of the complex is going to be 0. And that of the Br minus is going to be 0 as well. And then the change here is going to be minus S for the solubility, right? So because of the 1-to-1, I'm sorry, minus 2S for the solubility because of the 1-to-2 ratio between the silver bromide and the ammonia, if S is the solubility of the silver bromide. Here, the change here will be plus S for the complex, and here the change for the bromide is plus S, and therefore at equilibrium, you're going to have 1.50 minus 2S. Here you're going to have S, and here you're going to have S, right? So the Kf, or I should say, I'm sorry, that's not Kf, that's just K, right? Because that's the result of adding both equations. Okay, what's going on here? Okay, so the K expression would be the concentration of AgNH3 2 plus times the concentration of the bromide, all divided by the concentration of NH3 squared. So all we have to do from here is plug in these terms into this equation. And what would be the result? Well, because these two are equal, I'm just going to put S squared up here, divided by, squared, divided by 1.50 minus 2S, and all of this would be squared, right? And that would be equal to the K value, which is 9.04 times 10 to the minus 6. And basically, it's all algebra from here, because basically we need to solve for S. Now, let me just make this look proper. So this is squared, right? So what I would do in order to solve for S is to find the square root of both sides. Whoops, what did I do? Let me do this again. I'll find the square root of both sides here and here, right? And the reason why I can do that because this term here is squared, the numerator, and the denominator is also squared. So I'm going to need some more space again. So I'm going to erase some of this stuff here. And, okay, so basically, I'm gonna end up with S over 1.50 minus S, and that would be equal to the square root of 9.04 times 10 to the minus 6. So 9.04 times 10 to the minus 6. I find the square root of that. And according to my calculation, this works out to be equal to 3.01 times 10 to the minus 3. And then I will go through some steps. I'll multiply both sides by by the denominator here. I'm going to end up with S is equal to 1.50 minus S multiplied by 3.01 times 10 to the minus 3. And then when I multiply this by everything within this parentheses, I'm going to end up with 4.50 times 10 to the minus 3 minus, this should be 2 here, minus 6.02 times 10 to the minus 3 S, and that would be equal to 3.0, that's it. I'm sorry. What am I doing? Okay, so that's the result of expanding, what's the term? Distribution, or whatever the term is in math. And then what I would do is add 6.02 times 10 to the minus 3 S to both sides, because you want to group like terms on the same side of the equation. And I can clearly see that 6.02 is much less than 1. So continuing up here, you're going to get S being equal to 4.5. And this here should be 4.52, not 0. So S is going to be equal to 4.52 times 10 to the minus 3 M, right? That's a molar solubility. So that's basically how we get the B part. All right? Okay, any questions about that? How we got the solubility? Any questions? Okay. Now the C part is asking for the mass of silver bromide that would dissolve in 175 mils of 1.5 M ammonia. Now the solubility we calculated was 4.5. So this is the C part here. 4.52 times 10 to the minus 3 moles per liter. So what we need to do is find the equivalent in grams per liter, which means that we have to multiply this by the molar mass. And I looked at the molar mass already, and it is 187.77 grams. In fact, let me check to make sure that is true, just to be on the safe side. So let me do this. Molar solubility. Not molar mass, I'm sorry. Molar mass of silver bromide is what we're trying to get. So let me do this. Oops. Okay, so AgBr. Okay, so that's correct. 187.77 grams. So let me go back to this. So let me turn back my pen on. So this here is 187.77 grams per 1 mole of the silver bromide. So the mole units will cancel out here, but what we need to do now is find out the mass in grams that will dissolve in 175 mils. So that means I have to multiply this by 175 mils, but I have to convert that to liters, 1 liter over 1,000 mils, so that the liter units will cancel out, the milliliter units will cancel out, so the only unit that would be left would be the grams. So when I did that calculation, I got 1.49 times 10 to the minus 3 grams, all right? And that's basically how that is done. Now, going back to the B part, remember we calculated the solubility in ammonia being equal to 4.52 times 10 to the minus 3. If you compare that to the solubility in pure water, obviously we see a big difference, right? Basically, the solubility of the silver bromide is much higher in an aqueous solution of ammonia compared to pure water, right? Which makes sense because what will happen, as we saw, as we were doing the problem, the ammonia is going to form a complex with the silver ions, and therefore that will reduce the concentration of the silver ions, and therefore, according to Le Chatelier's principle, the equilibrium will shift in order to form more silver ions, and therefore would increase the solubility of the silver bromide, all right? So that's basically what happens in this case. Yes, ma'am? I'm sorry?
The 7.3 times 10. What do you?
Oh, that was from the previous part. That was from solving the A part here, calculating the molar mass of silver bromide in water. Okay, any other questions? Any questions out there in Zoom? Oh, somebody said something. Will the denominator, oh, I think, okay, yes, who is it? Mr. Spivey, yes. I think I made a correction on that. You're asking about this part right here, I think. I think I'm neglected to put a 2 there, but I corrected that. Okay, any other questions? Any other questions? Okay, so let me clear this. And what we're going to do now is start with the next chapter, which deals with thermodynamics. So let me bring up the PowerPoint here. So as you can see, the title here basically says entropy, free energy, and equilibrium. But basically, what we'll be dealing with here is the area of thermodynamics, right? And there's some things that you're going to encounter which you'd have encountered before in General Chemistry 1 when you did the chapter on thermochemistry. All right. So some of that information or some of the concepts involved will play an important role in this particular chapter, right? Now, the first thing we need to talk about is this term that you're going to see very often in this chapter, and the term is spontaneity, right? So in chemistry or in science, when we talk about a spontaneous process, it means something different from, our everyday language. People tend to think of something being spontaneous as something like, explosive, right? Or dramatic in terms of what you observe, right? In chemistry, in particular, when we say that a process is spontaneous, we're talking about a process that will occur without any assistance from anybody. It just happens, right? So here are some examples of spontaneous processes, right? And this is true in the case of physical and chemical processes, right? Water running down a hill, right? That is obviously a spontaneous process. You don't need to do anything for that to happen, right? It just happens, right? A lump of sugar dissolves in a cup of coffee. Again, that's a spontaneous process. At 1 atmosphere, water freezes below 0 degrees Celsius and ice melts above 0 degrees Celsius. So both the freezing and melting at the different temperatures are spontaneous processes. Heat flows from a hotter object to a colder object. So if you have two objects in contact with each other, one is hotter, one is colder, then there's going to be a heat flow from the warmer object to the cooler object. Again, that's an example of a spontaneous process. A gas expands in an evacuated bulb. Again, that's another example of a spontaneous process. Iron exposed to oxygen and water forms rust. That's a chemical example of a spontaneous process. So basically, spontaneity is basically describing a situation where a process will occur unassisted, all right? So the picture to the bottom right of this page is an illustration of that again. The skier going down the slope, well, he doesn't have to do anything to go down the slope, so that's a spontaneous process. But the skier that is moving up the hill, that process will be a non-spontaneous process. And typically what you'll find, and we're going to see this later on in this chapter, typically what you'll find is that in order for a non-spontaneous process to occur, then energy usually would have to be expended in order to make that happen, all right? And usually the energy itself would be derived from a spontaneous process, okay? So basically what we're saying here is that if a process is non-spontaneous, but you want to make it happen, then you'd have to basically couple it to a process which is spontaneous, all right? Okay, so here's another example of a spontaneous process. So let's say you have these two jars connected by a stopcock here, and in one jar you have a gas present, and then you release the stopcock here, and we all know what's going to happen. Basically, the gas will be spread between both jars until basically they're both equally filled, right? So that is an example of what we call a spontaneous process. Now, a non-spontaneous process would be the reverse, right? Where the gas in one of the jars is made to move into the other jar, and that would not occur by itself. Somebody would have to do something, or energy would have to be expended in order for that process to occur, all right? Okay, now, this begs the question, okay, can we predict, especially in the chemistry, in the context of chemistry, is it possible to make a prediction as to whether or not a chemical reaction is spontaneous? So what are the features that we would observe when it comes to spontaneous reactions, right? Now, one of the things that was looked at was basically whether or not the reaction is exothermic or endothermic. In other words, we look at the enthalpy change occurring for spontaneous reactions. And this is what we observe. So these are just a few examples, right, of spontaneous, all these reactions here are spontaneous processes along with their enthalpy change values, right? And what was observed, generally speaking, if you do a broad survey of reactions and examine the enthalpy change of these reactions, what you'll find is that most of these reactions are either exothermic, as in the case of the first two, or they're endothermic, but the value of delta H is a small positive value, right? So these are the two things that are observed when it comes to spontaneous reactions. They're either very exothermic, as you see in the first two examples, or they're endothermic, but the delta H value is small and positive, all right? But that doesn't really help in terms of making predictions in terms of whether or not a reaction will be spontaneous, right? So it turns out that there's another factor that comes into play when it comes to predicting whether or not a reaction is spontaneous. One of them is the enthalpy change, right? But the other one is a factor, a thermodynamic quantity that is called entropy, all right? So the question now is, what is entropy? Well, the actual definition is more complex than what we have here, but this can be a working definition for all purposes. Entropy is simply a measure of the amount of randomness or disorder a system may have, right? So basically what we're saying here is that the more disorder the system, the greater will be its entropy, right? So if the system has an order increasing, then the entropy would fall. But if the disorder is increasing as the process occurs, then the entropy would increase, all right? And the entropy can actually be measured. In fact, there are tables, including the one that I've published in Canvas. Let me just show you where we can find that. So let me go here, and let me go to tables, and the thermodynamic data, which is not published, so let me publish it now. Oh, it was already published. Okay. That one is an extra copy, which I need to get rid of. All right. So if you recall this table, well, those of you who had me in Chem 1, in Chem 1, we were only concerned with these values here, the enthalpy values for these substances, right? The entropy values are also given, right? So different substances have different entropy values, right? So just to give an example, highlight one or two examples. Aluminum oxide solid has an entropy value of 50.92. And please note the units. It's joules over Kelvin mole, right? And these are measured under standard conditions. Remember, standard conditions would be 25 degrees Celsius for temperature. And for gases, the pressure would be 1 atmosphere. And for solutions, it would be 1 molar, all right? So these are the entropy values that you can use under standard conditions for future calculations. So this is just showing you where they are. All right, so let me go back to the slide here. So if you have a process where there's a change in entropy, then we calculate that change by using this equation, right? The change in entropy would be the final entropy value minus the initial entropy value. So it's kind of similar to what you learned in General Chemistry 1 with respect to delta H, right? Delta H would be the enthalpy of the final state minus the enthalpy of the initial state, right? So if you have an increase in randomness, right, as you go from initial to final, then delta S, well, firstly, the final value would be greater than the initial value, which means that delta S would be positive, right? So this represents a situation where as you go from reactant to product, there's an increase in entropy, right? Now, of course, you can use your imagination in some instances to basically tell whether or not there will be an increase in entropy or not. For example, if you look at a substance, let's say water, and compare the solid state to the liquid state to the gaseous state, right? In the solid state, the structure is more ordered compared to the liquid state where the molecules will have more degrees of freedom. And that compared to the gaseous state would even be more ordered because in a gas, as we all know, the particles are moving more randomly with more energy, right? So for any substance, including H2O, the entropy of the solid would be less than the entropy of the liquid, which would be significantly less compared to the entropy of the gas, right? So this is just basically something that you can, a conclusion you can come to just based on what you know about the behavior of the particles, you know, in different states, right? So for example, if we look at the transition of H2O solid to H2O liquid, we can predict the sign. Maybe we can't, we definitely can't determine the value. We're going to talk about how to do the calculation of the change in entropy. But at the very least, based on what we know about the solid and liquid states of H2O, we can say that there'll be an increase in entropy as you go from solid to liquid, which means that delta S would be positive for that change, all right? Okay, any questions so far? Any questions concerning entropy that we have discussed so far? Okay, so here are just some other examples of situations where there'll be an increase in entropy. We talked about going from solid to liquid already. We all understand what that is all about. We also talked about going from liquid to gas. Again, in those two cases, there's an increase in entropy, so delta S will be positive. Here we have a situation where we have a solute dissolved in a solvent. That would also correspond to a change in entropy that would be positive. And this one might not be immediately obvious, but imagine, if you will, you have something at one temperature and then you increase the temperature to a higher value. Believe it or not, the change in entropy in that case would be also positive, right? If you think about, let's say, heating a metal like iron, right? At a lower temperature, even though it's in a solid state, the iron atoms will still have some movement and their movement would be generally vibrational, right? So if you increase the temperature of iron from, let's say, 30 degrees to 50 degrees Celsius, the amount of vibration would increase, right? And therefore, as a result, the entropy of the metal would be increasing. So therefore, as the temperature increases, the change in entropy increases. And that is true. I'll go out on a limb here and say that is true in every case, right? I can't think of any exception to this, where as you increase the temperature, the entropy of the substance or the system will increase, all right? Okay, so let's see if you understand this whole concept of entropy change, right? So the question is asking, how does the entropy of a system change for each of the following processes? And the first one is condensing water vapor, right? And just to help you out with this one, condensation is where you're going from, let me write this down. Condensation is where you're going from H2O liquid, I'm sorry, H2O gas to H2O liquid, right? That's condensation. So my question to you is, would that correspond to an increase or decrease in entropy? Decrease in entropy is indeed the correct answer. So therefore, delta S would be negative. All right, very good. What about forming sucrose crystals from a supersaturated solution? So in the case of the formation of crystals, you're going from, but I won't write down the formula for sucrose. I'm just gonna say you're going from an aqueous solution to solid.
Increase.
You sure with that? Think about it. Aqueous solution. A solution compared to a solid. Which one is more random? Or which one is more disordered? Is it the solution or the solid? Exactly, right? And the solid would be more ordered. So what would be the change in entropy in that case? Would it be, exactly, would decrease, exactly. So randomness decreases, which means that delta S would also be negative, all right? Okay, C, you're heating hydrogen gas from 60 to 80 degrees.
So like when it becomes disordered, that's when.
Entropy increases. If you're going from more ordered to more disordered, that's delta S positive. Because what you have to keep in mind is that S, the entropy, is a measure of how disordered the system is. All right? Okay. C, heating hydrogen gas from 60 to 80 degrees Celsius. Would that be an increase or a decrease in entropy? Increase, because of what I said earlier. Remember I said that increasing the temperature of anything results in an increase in disorder. So therefore delta S will be positive. I think I have one more here. Subliming dry ice. Now, I don't know if you know what subliming is, right? Or sublimation. Sublimation is basically going from the solid state to the gaseous state without going through the liquid state, right? So if you're going from solid to gas, would that correspond to an increase or decrease in entropy? Going from a solid to a gas.
Increase.
Increase, exactly. So therefore, as a result, and I think somebody just chimed in, yes, somebody said a large increase. Mr. Powers, right? So basically the answer is that there will be an increase, which means that delta S is positive. I think that's the last one. Yeah, okay. So if you understand that, then you should be able to answer number one in the assignment I'm about to give you. And for those of you out there in Zoom, I'm going to publish it now. If I've not done so already, but I don't think so. So let me go here, close that, go here, and go to assignments. And this is assignment number 6. So let me publish that now. Okay, so I'm going to open it up here. So you guys out there in Zoom should be able to download that assignment. Now, in this case, the question is giving you pairs of compounds, and they're asking you to tell which one has the higher entropy. All right? So, A, H2S liquid versus H2S gas. Let me turn on my pen here. Okay, so circle the one that has a higher entropy. So which one has a higher entropy in the case of A? H2S gas. What about B?
Sodium.
Sodium gas.
That's gay.
Yeah. What about C? H2O gas at 200 degrees Celsius. And D? Sugar dissolved in a cup of water. All right, so that's basically how we do that. All right, very good. Okay, let me clear this here and go back to the PowerPoint. All right, so okay, so entropy, as I said before, can be measured, and I showed you the tables. This is just a small sample, of course, of different substances and their entropy values. And basically, if you look at these, you can see the numbers correspond to what we were discussing just now, right? For example, if you look at the entropy values for H2O liquid and H2O gas, you see clearly H2O gas has a higher value compared to the liquid. Or if you compare bromine liquid and gas, you see the same pattern. Iodine solid and iodine gas, again, you see that the gas will have a greater value compared to the solid. Now, carbon and graphite are two forms of, graphite and diamond, are two forms of carbon, right? So they're both solids. So, you know, you would be able to, at least at your level, you know, just be able to determine which one has a higher value in terms of the entropy. It turns out that graphite has a higher value compared to carbon, right? And even in the case of one atom elements that exist in nature, like helium and neon, one can see that neon has a higher value compared to helium. The main reason for that is because the neon atom is larger and therefore has more randomness associated with it because it has more electrons and so on. So therefore, neon has a larger entropy value compared to helium. Okay. So entropy can be measured, and entropy is a state function. Now, state functions, just to remind you, are basically properties that of different substances that are dependent on several things. Things like the state and temperature and all of that. All right. So you've met some state functions before, like enthalpy, volume, pressure. Entropy is also a state function, and just like any other state function, the change in that particular state function, entropy, is based on only the initial and final state and not dependent on how you get from the initial to final state, right? And this diagram here is basically illustrating what we mean by that. If you have two hikers, one traveling this pathway and the other one traveling a longer pathway to the peak, the change in the distance in terms of the height would be the same. So basically, the height of the mountain is analogous to the difference in entropy values between the initial and final states, all right? Okay, so just to remind you of the first law of thermodynamics, energy can be converted from one form to another, but energy cannot be created nor destroyed, right? This is something that you would have learned in your general chemistry 1 class. The second law of thermodynamics, which I'm going to introduce to you now, says that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process, right? So what does that mean? That means that for a spontaneous process, the entropy, the sum total of the entropy of the system and surrounding, which comprise the universe, would be greater than 0, right? That was true for a spontaneous process. However, in the case of an equilibrium process, then the change in entropy of the universe would be equal to 0, all right? So that's basically what the second law of thermodynamics is saying, all right? So how do we calculate the standard entropy of a reaction? It's very similar to how you calculate change in enthalpy of a reaction. If you have a table of values, it's very easy, right? It's basically the sum of the total entropy of the products based on the equation minus the sum of the entropy of the reactants, right? So it's products minus reactants, just like in the case of enthalpy. So in this hypothetical example, where the lowercase letters represents the coefficients and the uppercase letters represents the formulas for the different substances, then you can calculate the change in entropy of the reaction using this equation right here, right? This represents the sum of the entropy of the products. This represents the sum of the entropy of the reactants. So it's products minus reactants, right? Or you can simplify it using this expression right here, okay? So based on what we have just looked at, we can answer questions such as the one that you see here. What is the standard entropy change for the following reaction at 25 degrees? And it gives you the balance equation. Of course, you need a balance equation to begin with, right? So what you'd have to do is you'd have to consult the tables, right? So when you consult the tables, in terms of looking up the entropy values for these different substances, this is what you get, right? The value for carbon monoxide, carbon dioxide, and oxygen are given right here, right? And then now, you set up your equation. Remember now, it's the sum of the entropy of the products. In this case, it's only one product, which is carbon dioxide, which you have to multiply by 2 because you have the coefficient here, minus the sum of the entropy of the reactants. Again, you have to multiply the carbon monoxide here by 2 because of the coefficients here, and then you add that to the value for the oxygen. And then that sum, you're going to subtract from 2 times the entropy of carbon dioxide. So from here, it's a matter of plugging the numbers in. So when you plug the numbers in, you're going to end up with your answer being minus 173.6 kilojoules per mole. All right, so that's basically how you're going to calculate the enthalpy change of any reaction if you're given a balanced equation. So based on that, which we just covered, I'm not going to go through this with you guys, but you guys should be able to do this on your own. You should be able to do questions 2, question 3. Let me see here. Okay, question 2 and question 3, based on what we have just done, all right? So I leave you to do that. If you have any problems doing them, then come and see me or call me on Skype during my office hours, and then we can discuss that, all right? Okay, any questions about this example? Any questions? Any questions? Any questions? Oh, somebody has a question here. Oh, I thought somebody had a question. All right. Okay, continuing. Okay, so we can make again some predictions about delta S being positive or negative based on a balanced equation, right? For example, if you have a reaction where it produces more gas molecules than it consumes, then we know that delta S is positive, right? So if you have a balanced equation and you see that the total number of moles of gases on the product side is greater than that on the reactant side, then we know that delta S is going to be positive. If you have the reverse, right? If the number of moles of gas on the reactant side is greater than that on the product side, that means that delta S would be negative, right? If there's no net change, right? So like for example, if you have this reaction here, nitrogen plus oxygen to form NO2, or NO, I should say, right? In this case, you have 2 moles of gas here, you have 2 moles of gas here. You cannot make a prediction just by looking, right? The most you can say is that delta H, or I should say delta S, is either going to be positive or negative, but very, very small, right? And in order for you to calculate the delta S value, you have to go to the tables and do like what we just described, all right? Okay, so in this case here, let me see if you can answer this question. What would be the sign, not the value, just the sign of delta S for this reaction? Will it be positive or negative? Exactly, it will be negative because as you go from left to right, you're producing less gas molecules. You have 1 molecule of gas on the left, you have none on the right, so therefore delta S is going to be negative. All right? Okay. So, if you're given questions of this type, there's no need for you to do all the calculations. You just look at, those sort of changes as you go from left to right of the reaction. Okay. So, as far as entropy changes in the surroundings is concerned, it's related to the entropy change in the system. So if you have an exothermic reaction which generates heat, then that means that the entropy of the rest of the universe would increase as a result, right? So therefore, delta S of the surroundings would be positive. On the other hand, if the reaction is endothermic, which means that it's absorbing heat from the system, then the change in entropy of the surroundings would be negative, all right? And this leads us now to the third law of thermodynamics, which says that the entropy of a perfect crystal is 0 when the temperature is equal to 0 Kelvin, right? So this is illustrated in this particular graph right here, which is a plot of entropy versus temperature in Kelvin. And basically they're starting from 0, which would mean it's a perfect crystal. What a perfect crystal means is that the particles have 0 kinetic energy. No translational energy, no rotational energy, no vibrational energy, right? So therefore, basically, it has 0 energy here. As you increase the temperature, the solid entropy would increase until you get to the melting point, and then there's going to be a big jump in entropy as you convert from the solid to the liquid state. And then as you continue to increase the temperature, the entropy will continue to increase until you get to the boiling point. Again, is going to be a big jump in the entropy of the liquid until you get to the gaseous state, and then the entropy will continue to increase as you increase the temperature of the substance, right? Okay, so now, what time is it, by the way?
3:50.
Okay. Oh, by the way, this chapter is relatively short, so I anticipate that we'll be finished with this chapter by the next class. If not today's class. Okay. So remember now, we talked about, or the question we were facing was, how do we predict the spontaneity of a reaction? And as I said before, there are two factors which affect the spontaneity. One is enthalpy, which you learned about in general chemistry 1, and the other one is entropy, which we just covered, right? So it turns out that there's a combination of those two factors that would result in us being able to predict whether or not a reaction is spontaneous. And that has to do with another state function known as the Gibbs free energy. Now, the actual definition of the Gibbs free energy is the energy associated with a chemical reaction that can be used to do work. And it turns out that the Gibbs free energy is related to both enthalpy and entropy according to this equation right here, right? Delta G for a system, which is a free energy change of the system, is equal to the enthalpy change of the system minus T times the enthalpy change of the system, all right? And please note that delta H, or I should say the temperature, must be expressed in Kelvin, all right? So if you're given a temperature in Celsius, you have to convert that to Kelvin, right? And delta G is basically what you use to tell whether or not a reaction or process is spontaneous. In that, if delta G is negative, right? If delta G is negative, then the reaction will be spontaneous in the forward direction and non-spontaneous in the reverse direction, all right? If delta G is positive, the reaction is non-spontaneous in the forward direction and spontaneous in the reverse direction. And then we have a third possibility where delta G is equal to 0. If delta G is equal to 0, what that means basically is that the system is in equilibrium. All right? So these are basically the three possibilities that can exist as far as delta G is concerned. And this is how you're going to use delta G to predict whether or not a reaction is spontaneous, right? Okay, so get this out of the way here so I can see what I'm dealing with. Okay, so again, we can have measurements of what we call the standard free energy, which is the free energy under standard conditions. And again, going back to the table that I showed you guys, let me see if I can go back to it. There is a third column in the middle of that table, which gives you the enthalpy of, not enthalpy, I'm sorry, the free energy of formation. Where's that table? Okay, so this here, the column in the middle, gives you the free energy of formation of the different substances, all right? Formation, if you remember, deals with situations where you're forming the substance you're forming one mole of the substance from their constituent elements, right? And one thing I want to point out here is that when it comes to the elements themselves, like aluminum, like you have aluminum, you have arsenic, you have barium, you notice that the free energy of formation of these substances is 0, all right? Just like in the case of enthalpy, all right? So let me go back to the PowerPoint here. So this is where you're given a definition of the standard free energy of formation of a substance. It is a free energy change that occurs when 1 mole of the compound is formed from their elements under standard condition, right? So this is how we calculate the free energy change of a reaction. Again, very similar to what we discussed with respect to change in entropy. It's a total sum of the free energy of the products minus the total sum of the free energy of the reactants. And as you can see, that is represented here and here in this chart, right? So remember again, these are the conditions for standard state, right? If there's a gas involved or gases involved, the temperature, or I should say the pressure is 1 atmosphere. If the liquid and solid will be pure. And for elements, the enthalpy of formation, not the enthalpy, the free energy of formation will be 0. And if your solution is involved, then the molarity is 1 molar. All right? Okay. Okay, so based on what we have just covered, then you should be able to answer this question. They give you the balance equation. So, and they're asking for the standard free energy change. So again, what you'd have to do is go to the tables and look up the values for the different substances. In the case of carbon dioxide, this is the value of the free energy of formation of carbon dioxide. This is the value for water, and you notice that you multiply, in the case of carbon dioxide, you multiply its value by 12 because of the coefficient of 12. In the case of water, you multiply its value by 6, and then you minus the free energy of the sum of the free energy of the reactants. Now you'll notice that there's only one reactant indicated in terms of its value being given here, and that's for C6H6, which is benzene, right? We multiply that by 2. We do not need to include the value for oxygen because oxygen is an element by itself, and therefore its free energy is 0. So that's why you do not see it included there. Yes, ma'am.
So would that be true for all?
For all elements, not combined with anything else, right? Okay, so you plug those numbers in and you get the minus 6,405 kilojoules per mole as the free energy for that reaction. And again, let me see what questions would apply based on what we have just covered. Okay, so at this juncture, you should be able to do question 5. Okay, in fact, I think I'm going to help you with at least 5A. Okay, so let's see here. Let me go to this here. Okay, so question 5A says, using the values of delta S and the enthalpy of formation, calculate delta G for each of the following. Now, in this case here, they're not asking you to calculate delta G directly from the delta G values in the table. They're saying using delta S and delta H standard, right? So you'd use a table, but you're going to use these values here, right? So the first thing we need to do is calculate the value of delta S. Delta S will be equal to the standard will be equal to S standard of the lead 2 chloride plus, not plus, minus the sum of the entropy standard of lead solid plus the entropy standard of chlorine gas. So now we have to consult the tables. So let me see here. So let's see here. So I'm looking for the value of lead 2 chloride. And this is arranged in alphabetical order. So should be able to find, okay. Okay, looks like, interesting. We don't have lead 2 chloride here. So you know what I'm going to do? I'm going to look it up. But that value should be given, like if you're given an exam and, you know, it's not available in the table. So what I'm looking for the standard entropy value of PbCl2. Let's see what comes up. Okay, so according to, let's see. Okay, let me check this here. Okay, according to this here, this is equal to 139.4 135.98. So let me go back. So this would be equal to 135.98 joules per mole Kelvin. All right. Okay, and then now we need to find the enthalpy, the entropy value for lead solid. So lead solid is right here. Which is equal to 64.81. So minus 64.81 joules per mole Kelvin. And then we need to find the value for chlorine gas. And also, let me just say this, I probably should have stated this before. Pay attention to the state symbols, right? Whenever you're doing these problems. So since the question says chlorine gas, that's what I'm going to look for, chlorine gas, which is right here. And the value for chlorine gas is 105.68. So plus 105.68 joules per mole Kelvin. All right, so let's see what this gives. So 64.81 plus 105.68, and then I'm going to subtract that from 135.98. And according to my calculations, and please correct me if I'm wrong, according to my calculation, this works out to be minus 34.51 kilojoules. Not kilojoules, I'm sorry, joules per mole Kelvin. So this would be joules per mole Kelvin, right? So that's delta S for the reaction. And then now we do the same thing for delta H standard, which would be the enthalpy standard of PbCl2, which again I have to look up because it's not in the table, minus the enthalpy standard of Pb solid, plus the enthalpy standard of Cl2. And somebody's asking a question in Zoom. Let's see here. Okay, let's see. Okay, yes, Ms. Hersey, what's your question?
So for the Cl2 gas, never mind. I might be looking at something different. Hold on. Sorry.
No, don't apologize. What's the question? Or is the question answered in your mind?
On the table, are we using the entropy value?
Yeah, that's what we're doing. That's what we're doing here.
So the entropy value for the Cl2 gas is actually 223.07.
All right, okay, let's see. Let's see. Cl2 gas. Oh, okay, you're right. So let me correct that. So that's what, okay, hold on, let me take out my eraser. So this is incorrect. And it should be what was I looking at? I don't know, anyway. 223.07. And that would be joules per mole Kelvin. So that means this answer is incorrect. So let me erase this here. And let's see what the answer is. So that would be okay, that would be 64.81 plus 223.07, and then I'm going to subtract from that, or that from 135.98, 135.98. Okay, so the answer, no, something is wrong here. Let me do this again. 64.81 plus 223.07, and then subtract that from 135.98. Come on, one more time. 64.81 plus 223.07. Okay, the answer I got, and again, please correct me if I'm wrong. Whoops. The answer I got is minus 151.90 joules per mole Kelvin. Okay? Okay, thank you, Miss Percy, for that. Okay, so we do the same thing for the enthalpy. So as I was saying, we need to, I need to look, yes, ma'am, sorry.
Do we need 5 seconds for that, or?
Well, actually, I round off to 2 decimal places because remember, when you're adding or subtracting, right? So there are 2 decimal places right across the board, so therefore 2 decimal places there. Okay, so as I said before, I need to look up the standard enthalpy value of lead-2 chloride because it's not in the table. So let me see if I can. So I'm going to look for the standard enthalpy value for lead-2 chloride. And let's see here, search. Okay, what's the enthalpy? Okay, here it is. 136.0 kilojoules, joules per mole Kelvin. So, so this is going to be 136.0 joules per mole, kilojoules per mole. Minus, okay, now for in the case of lead, let's see, scroll down. Okay, lead solid. The value is 0, of course. Why am I looking it up? It's 0, lead by itself. Right, so in the case of lead, it's 0, and in the case of chlorine, it's 0 as well. So this is going to be 0 plus 0. So this works out to be 136.0 kilojoules per mole, right? But the question is asking for delta G. Remember now, delta G is equal to delta H standard minus T delta S standard, right? So basically, let me erase, I need some space. So let me erase up here. So basically, delta G standard would be equal to delta H, which is 136.0 kilojoules per mole, minus T, which is 25 degrees Celsius, which is 298 Kelvin, because we're talking about standard temperature, multiplied by S, which is this right here, minus 151.90, and this is joules per mole Kelvin. But we need to multiply by something else because we need to keep the units consistent. Because we have kilojoules here, I'm going to convert this joule unit to kilojoule. So 1,000 joules down here, and 1 kilojoule above. All right, and that will give us the final answer. So let me erase this right here. And okay, so let's see. I'm going to do the 298 multiplied by 151.90 minus divided by 1,000. And then I'm going to put a minus sign in front of that, and then I'm going to add that to 136.0. And according to my calculation, the answer becomes 181.3. And that would be kilojoules per mole. So that's basically how you do that, right? And if you understand that, then you should be able to do the other parts, the B part and the C part as well. All right? Okay. Any questions? Any questions about this? Any questions? All right, let's see what's next. Oh, let me clear this first. This, let me go full screen. Oh, okay. I think this is going to be the last thing we're going to discuss concerning free energy for today, at least. Okay, now remember, free energy is used to make predictions as to whether or not a reaction is spontaneous, right? So remember we said that if delta G is negative, then the reaction will be spontaneous. If delta G is positive, then the reaction will be non-spontaneous as written, right? Now what we're going to look at here are different situations where the signs of delta H and delta S will be different and how that affects the sign ultimately of delta G. So we're going to start off with a situation where delta H is positive, right? And delta S is positive, right? Now, if delta H is positive, right? Remember now, delta G is equal to delta H minus T delta S. So if delta H is positive and delta S is positive, the question now becomes, okay, based on those two facts, can you make a prediction as to whether or not delta G would be positive or negative? And the answer is, it depends. And what do I mean by it depends? It depends on the temperature. Because if you think about this equation, if you think about the math or the algebra behind this equation, right? If T is relatively large, right? And delta S is positive and this is positive, that means that this part here, right, would be greater compared to this part here, which means that delta G would be negative, right? So at high temperatures, delta G would be negative because when T is very high, this part would be greater than this part, which means that delta H minus T delta S would be negative. So let me just write a little note here. For this part, for this here, if temperature is high, T delta S would be greater than delta H, I'm sorry, which would mean that delta G would be negative, which means that the reaction will be spontaneous, right? Now, if T is low, then the opposite is true, right? In fact, let me write that here. If T is low, then delta H would be greater than T delta S, which means that delta G would be positive. Delta G would be positive, not negative. I don't know why I did that there. Delta G would be positive. And if delta G is positive, of course, the reaction will not be spontaneous, all right? So that's what happens if delta H and delta S are positive. At low temperature, the reaction will be non-spontaneous, but at high temperature, the reaction will be spontaneous, all right? Okay, so let me clear this here. And let's talk about a situation where delta H is positive and delta S is negative. So again, you have to think about the math behind this equation right here. If delta H is positive and delta S is negative. Now, if this is negative, that means that this negative sign multiplied by this negative sign is going to be positive, right? So what does that mean? That means that delta G is always going to be positive, which means that the reaction would not be spontaneous in the direction that it is written, right? At all temperatures, delta G would be positive, right? Now, in the case where it's reversed, right? If delta H is negative and delta S is positive, that means delta G will always be negative. which means that the reaction will always be spontaneous, regardless of the temperature, all right? And then finally, in this case where delta H is negative and delta S is negative, basically what that means is that if the temperature is low, that means that this part here, if delta S is negative, would be positive when you multiply by this, and this is negative, and therefore, as a result, at low temperatures, the reaction will proceed spontaneously because delta G, as a result, will be negative. And then the reverse will be true if the temperature is high. In that case, delta G is going to result in being positive, which means that the reaction will not be spontaneous. All right? Okay, so that's basically it for today. I'm not going to go into this right now. So that will be for today. Let me just see if there's anything else you guys can do in this assignment here. Okay, so yeah, so far you should only be able to do the questions I told you about. And we'll continue our discussion next class, all right? All right, that's it for today. I don't think there's anything I have to say by the way for now. Oh, let me get those persons who came in late before I forget. Okay, let me bring this up here. Is Lucky, I don't see Lucky. Luna Sanchez, okay, she's here. Macias is here. Renfro, I don't see Renfro. Salvador, I don't see Salvador. And I got Spyberry. Okay, so that's it for today, folks.
Yeah, that things lab. Each group have to like be a person.
One person from each group can just bring in, you know, the water, yeah. You too.
Question.
Yes,
For
ma'am.
the Pensacola thing,
Mm-hmm.
I already told you that conference going on,
Mm-hmm.
but the last day, are you guys still doing something over there in Pensacola?
Okay, so, and this is based on what happened the last time we went there. What happened is that we're gonna leave here early in the morning, and then we're gonna get there at about midday, because we're gonna leave here like 6 o'clock in the morning. And then there'll be some events for us there, you know, introduction, blah, blah, blah. And then we stay overnight, and then we check out of the hotel the next day, and then we meet in the morning again at IHMC, and then activities continue until about midday, and then we leave after that. So that's basically the whole.
After midday?
Yeah, because we have to get back here, you know, by the evening. We're not staying over there for 2 days, just one,
Yeah, of course.
just one night.
Okay, and Pensacola is like 5 hours or?
About 5 to 6 hours, if I remember correctly, yeah.
Okay. Yeah.
Why, you're thinking of driving up there?
Well, no, I cannot drive up, by my own that long. But I was just thinking, if I was able to go and then come back, because one of the things in our conference, since we're hosting it, we have a ceremony, an award ceremony
Mhm.
for the colleges, and it's gonna be at Silver Springs, but it won't happen until like the evening.
Oh, okay, that's what you're
Yeah,
saying.
but we still have sessions going on in the morning here. So
Oh, okay. Yeah, that's
we'll try to
basically-
work something out, so it's
Yeah.
okay. All right, well, thank you. Have a good one.
Yeah, you too.
Oh, also, the link you put for the internship opportunity, it takes me straight to,
It should be a PDF document. You mean the one that I posted yesterday? About the water, aquatic stuff?
yes.
It should be a PDF document.
Okay, I'll
Yeah.
check back in. Thank you. Have a
Yeah,
good
no
one.
problem. Okay, for you guys out there in Zoom, I'm